Okay, so we'll start now. So I'll first of all I'll finish this one example here in the part 3 of chapter 6, and then we'll move on to the part 4 of chapter 6. Okay. So last time we have been dealing with the rotating platform, right? So and then I show you from a couple of different setups, right? So how the centrifugal force and the Coriolis force will affect the trajectories of the particles, so in the rotating frame, right? So this exercise or this example here again will deal with a rotating platform. You can see, and then what we do is that you can see that we set up a pendulum. Okay, so on this platform, okay, and so you'll see that, so in principle we will have to consider both centrifugal force and Coriolis force, but this problem is actually set up in a way that we don't need to worry about the Coriolis force, as you'll see. So the setup is like this, right? So you have these two supporting a rod here, and then this pendulum is composed of, you can just consider that the entire pendulum is made of a piece of a rigid metal, right? So you can see that this T-shaped thing. Okay, so just imagine that this whole thing is a rigid body. Okay, so it's a piece of metal, and then at the end of this T-shaped structure, you attach a mass M. Okay, so now you just consider this one as the same simple pendulum as we always consider, right? So this M, so if the whole thing is not, if the platform is not rotating, right, so this M will just do a pendulum motion like this. Okay, and because of the fact that, as I said, this whole thing is a rigid body, so this mass is only allowed to swing like this, right? So but not in the other directions. Okay, so now if the rotating platform, right, so it's rotating, then you could imagine that while this is doing this pendulum motion, right, so and in fact the mass is also rotating. Okay, so the question here asks us to study, right, so the frequency of this pendulum. Okay, so if we have just a simple pendulum, right, so you understand that the frequency is just sorry, the frequency, if there's no any rotation, it's just square root G divided by L, right? So how is it different when we have this rotating platform? So that's the question. Okay. So of course, we are going to use the rotating frame, right, so to help us. So I'm going to draw a picture again. So just imagine that you're looking at this pendulum, right? So from this side, so such that now the plane of the motion is just along this page. Okay, just along this page. Doing motion like this. Okay. All right, so now we need to consider the forces, right? So the real force, of course, is always there, is the rate, right? So I always have this mg here, and the tension. So what about the fictitious forces? So remember, right? So the whole thing is rotating about this vertical line here. So then you understand that the centrifugal force would be away, always away from the rotation axis, this way. Right. So this is the F centrifugal. So what about the, okay, so I might be, the notation may be a bit confusing here because this is omega, this is also omega. So let me just call this capital omega, okay, just to avoid the confusion. Small omega is for the frequency of the oscillation. So what about the Coriolis force? Okay. So at a particular moment, let's say at a particular moment, the velocity of this mass is, say, going this way, right? So or the other way, it doesn't matter. It's just along this plane, right? And the Coriolis force, if you do omega cross v, right? So what would you have, right? So you, for the omega vector, so this would be the omega vector. Right? So you know that the omega cross v must be a vector that is perpendicular to this page, right? So there is indeed a Coriolis force acting on the pendulum, but it is not really going to affect its motion, right? So because of the setup that I have here, it does not allow this mass to go away from this plane, right? So because of this setup, this is the rigid body, okay? So therefore, even though I always may have a Coriolis force that is actually pointing away from the plane, but the motion of the ball is still along the plane only. Okay, so due to the original setup that we have a constraint. Okay, so therefore, even we have Coriolis force, we don't need to worry about that. Okay, but it's there. Okay, it's just away from out of the page. Okay. Okay, so but now come back to the centrifugal force. Okay, so the centrifugal force is playing a role to the motion of this pendulum. Okay, so if I don't have this centrifugal force, right? So you still remember that the force that is actually relevant is this component of mg, right? So it's the mg sine theta, right? Mg sine theta. So what the equation of motion is, that is the m, right? So L squared let me just write ml theta double dot, right? So the acceleration of the mass, right? So in the tangential direction, L theta double dot, that would be equals to the this term, right? But if you just write down this is just the original simple pendulum that you have learned before, right? So now, if you look at, right, so if you look at this direction, right, so now you not only have this mg sine theta, you do have also have a component from the centrifugal force. Okay. So this would be, so the component of this centrifugal force along this line, what is that? Right, so that would be F centrifugal cosine theta. Right. So this is the additional term that will eventually change the oscillation frequency of the pendulum. Okay. So then what is this F centrifugal? So that would be omega cross omega cross R, right? So the direction you know already. So then the magnitude would be omega. So let me just write it here. Right, so that would be omega cross R. And the R would be a vector, right? So pointing from the center of the rotating platform to the mass, right? So this R, the length of this vector is just this, right? So what is this? This is, well, so again, it's just L sine theta, right? So that the magnitude of this whole thing would be just capital omega square times L sine theta. Right. So of course, I have a factor of m like this. Okay. Okay, so then the whole thing, let me simplify the whole thing, right? So then I have the whole thing equals to minus mg sine theta plus m capital omega square L sine theta times cosine theta. So that would be 1/2 of sine 2 theta. Right. Okay, so now again the same old trick, right? So the now we know that theta is very small, right? So then that means that this sine theta is approximately equals to theta, and then this sine 2 theta would be approximately equals to 2 theta, right? And then just group the whole thing together. So you have a factor of theta, and then the entire thing in front. Right, so what do we have? So actually, let me first of all just cancel this m, right? So then you will have this e minus L capital omega square divided by 2, right? And oh, this 1 divided by 2 should also cancel by this 2. So actually, I don't need a 2 here. Okay, like this. Right, so therefore, the final answer is that the theta double dot is approximately equals to minus G minus L omega square divided by L theta, right? Like this. So therefore, the frequency, the angular frequency of the oscillation would be square root of this thing. So like this. Right. So it's getting smaller compared to just the square root G divided by L. Okay. So the faster you rotate the platform, then the smaller, actually the smaller the frequency that you'll get. Okay. And that's because of the fact that the faster you rotate, right? So the stronger the centrifugal force you have, then effectively you will have a weaker restoring force, right? So for this simple harmonic motion. Okay. And one interesting you can also notice is that at some point, if you make the rotating platform rotate so fast that this capital omega being greater than this factor here, then you no longer can support a simple harmonic motion. Okay. Okay, so then this is the example that I want to talk about for this part. And okay, so this one I'll just skip this. Like this one you can try by yourselves. This one should be very easy. Okay. Okay, so now let me go to the part 4 of the chapter, and then this is also the last part that would be covered in the final exam. Okay. So after I finish this, and I'll talk about something else, but those things won't be in the final exam. Okay. So actually, one thing here is that I uploaded this part of the chapter right before the lecture this morning. Okay, so the one that I uploaded last night had some minor mistakes, and so if you want to get the most updated version, you should do it again now. Okay. Okay, so so far we have learned, right? So how to express the fictitious forces in the rotating frame, but we really didn't have a lot of examples to show you why it is helpful, why it is useful for us to solve problems. Okay. So then in this part of the chapter, basically it just gives you one class of examples that why we want to use rotating frames sometimes, right? So, and it is all due to the fact that the Earth itself is a giant rotating system, and we are all living on the surface of the Earth, right? So, and in this context, right? So it really makes sense that we want to use a rotating frame. Okay. So then in this part of the chapter, right? So it's all about, right? So a particle, right? So moving on the surface of the Earth, right? So we don't really notice that we are rotating, but in fact we are all living on this giant rotating system. Okay. Okay. So before I actually go to set up the rotating frame, okay. So specifically for the Earth's surface, I need to go back to talk about the rotating frame, the transformation between the fixed frame and the rotating frame. Okay, so because the coordinate system, the frame that we are going to set up is slightly different from what we had in the last part of this, in the previous part of this chapter. Okay, so recall what we had in the previous part of the chapter, right? So what we had is that I have this black fixed frame and then this red rotating frame, right? So, but in this case, in that case, we were setting up both coordinate system to share the same O. Okay, so the same origin, right? So now you imagine that I'm going to set up the rotating frame in a slightly different way now. Okay, so just look at the picture on the right, right? So again, you just imagine that I have a rotating platform, right? So, but this time, right? So previously, you just imagine that both of your observers are standing at O, right? So, but now the rotating observer, you just imagine that you have your rotating observer to be standing kind of at the edge of your rotating platform, right? So, and then now this is the new origin. So this O prime is the new origin for this rotating frame. And then this red frame, right? So is actually the origin of this red frame. This O prime is actually moving. Right? Just imagine that after some time, right? So the O prime will be somewhere maybe here, right? So and then at that time, right? So your basis vector will be like something like this. Okay. Right. So and at that time, this R will be here. Okay. Right. So this capital R. So I forgot to mention this capital R would be the position vector of the O prime itself. Right. So with respect to the fixed coordinate system. Okay. So therefore, now you can see that there are actually really two things are going on. Right. So one is that now the origin of the rotating platform itself is moving, or is moving, changing position as a function of time, and then at the same time, the basis vectors are rotating. So two things going on now. So instead of just the pure rotation here. Okay. So then now again, I'm going to talk about a particle, right? So moving in space, and I want to just describe that using the rotating coordinate system, right? So now suppose I have a particle like somewhere here. Okay. Okay, so but in this picture, it looks like that the particle itself is already outside of the rotating platform, but you can just kind of imagine that actually this rotating platform is infinitely large, right? So, but anyway, so this particle itself can be doing anything, right? So it can be moving this way, that way, this way, right? So it does not have to be follow the exact same rotation like this, right? But anyway, so it can do anything. Now, if I want to describe the position, set up the position vector, right? So set up the position vector is that for the fixed frame, then the vector that I will draw is something like this, right? So it will just be this vector here. I'll just call this, right, small r, right? Okay, so now if I want to describe the position vector of this same particle, right? So by according to the rotating frame, so this time I will have to draw a vector like this. Okay, R prime. Right, so that is in the previous situation. Okay, so the position vector for the particle would be just referring to the same vector. Okay, so but here slightly different. Okay, one is given by R, the other is given by R prime. Okay, so this is just draw the picture one more time here, and now just by vector addition, right? So you understand that this blue R is just given by this capital R plus R prime. Okay. Okay, so then you know where we should be going, right? So again, we want to relate the velocities in the relation of the velocity in the two frames, and then the relation of the accelerations in the two frames. Okay. So then taking the derivatives on both sides, right? So like this. Again, so now again pay attention to the subscript, right? So remember in the last previous part of the chapter, I told you how to take care of this subscript fix and the subscript rotates, right? So just start from the fixed frame, right? So do the derivative, right? And then now the second term over here, right? So I want to express it in the rotating frame, right? So then this, you remember that this d dt with the subscript fixed would be equals to d dt with the subscript rotate plus omega cross that vector, right? So the same trick is applied here, right? So this one becomes these two terms. Okay. So then next, acceleration, right? So second derivatives. So second derivatives, then you can see that I really just have the same trick here, right? So remember that this last three terms really are just the exact same as what we had in the previous part of the chapter. Okay. Now the additional term here is this d capital R dt, right? And here is the d square capital R dt squared. Okay. So then this is the term that you didn't see in the last previous part of the chapter, right? And now remember, so what this capital R is doing, right? So this, the only time dependence of this capital R is given by this rotation, right? So that's the only time dependence part of this R, right? So this capital R itself is not doing other things. It's not going to change length or anything. So therefore, right, so this d capital R dt is given by omega cross R. Okay. And then this d square R dt square would be given by this omega cross R. Okay. So then I'm going to just write down the final result over here. Okay, so what I do here is that you can see that I kind of combine the first term and the last term together, right? Because the first term becomes this omega cross R, capital R, and this one is omega cross R prime. Then I can just group them together. That's omega cross R prime plus capital R. Okay. Right. So then now look at this, right? So it looks very similar to what we had before, right? So it's just that this now this is with this additional capital R here. Okay, so now let's actually talk about the Earth, right? So we are going to again set up a fixed frame and a rotating frame. Okay, so for the Earth. Okay. Okay, so the fixed frame that we are going to set up for the Earth is over here. Okay, so the origin of the fixed frame is right at the center of the Earth, right? So you can see and then the z-axis, right? So just pointing to the North Pole, and then this is the x and y along the plane, okay, so of the equator. Okay. So and then now the other frame that will be at the Earth surface. Okay, so and one thing here. Okay, so you clearly you can see the two frames, but now this time I'm going to use the prime frame to denote the fixed frame, but then the unprimed frame to denote the rotating frame. So but previously we did the opposite, right? So the fixed frame is the one without the prime, and now and then previously the rotating frame is the one that with the prime. So here we do the reverse because in the upcoming examples we will be basically mostly just using the rotating frame, right? So and because that's the frame that we use in majority of the time, then we just for convenience we just say that the unprimed frame is the one that we use mostly, right? So then that's why we reverse the convention. Okay, so just take notes here. Okay. Okay, so but anyway, so the rotating frame would be right over here, right? So is that just imagine that you're standing, just like standing here, right? So standing at a particular point of the Earth's surface, and then you are always rotating, right? So with this part of the Earth's surface, and then you can see that how I point out the three basis vectors. Okay, and right, so the z is the one that is pointing away from the center of the Earth, right? So just pointing to the sky, right? And then you can see that this x vector here, it would be just pointing along a longitude line, right? So and then the y is just pointing along a latitude line. Okay. So in fact, it might pretty much remind you of the spherical coordinates, right? So if you remember the r hat, theta hat, and phi hat, right? So really just corresponding to these three, right? So the setup indeed very similar to the spherical coordinates. Okay. So however, there's one convention that would be different, right? So in spherical coordinates, so you have an angle that is the so-called the polar angle, which is this one, right? So the angle between the vertical line and this line here. But here we won't be using this angle, right? So instead we will be using this angle called lambda. Okay. Just a convention, right? So we talk about the latitude, right? So the northern latitude and the southern latitude is we use this lambda to describe that. Okay. Okay, so then now you see why I needed to talk about this set up, right? So now you can see that we do have two coordinate systems that are not sharing the same origin, right? And even more, right? So in fact, right? So in this case, the direction of the z vectors are not even parallel anymore, right? So in this case, I in this picture I still do have the two vectors being parallel. Okay, so but in this, right? So now is not even the case, right? So, but well, you understand that the direction of this z vector is really depends on where you are standing at, right? So at this Earth surface, right? So if you are standing well, so if you are standing somewhere, right? So at the equator, right? So you understand how your free your free vectors would change, right? So with like this, okay, was like this. So it's like right. So then this would be your z vector, right? So and then now the x will be pointing down, right? So and then this would be y. Right. Okay, then now, right? So let's actually go to consider the fictitious forces. Right. So this is the equations that we have already derived, right? And now we need to substitute the appropriate capital R, right? So and also the omega vectors, so into this this equation. Right? So again, remember, now we in our convention now, right? So the unprimed frame is the rotating frame. So that's why now everything on the right hand side don't have a prime, and then the one on the left hand side has a prime. Okay. So I'll talk about how to substitute the capital R and the omega later, but here I'll just again just write out the form of the force. Okay. So again, you see how this one works is that I'm going to, right? So just in this equation, again, I'm just going to just keep the MA term, right? So on the right hand side, and then move these two terms to the left hand side. So the whole thing on the left hand side, I'll call this effective force, right? So then this effective force would be this F real, which cause the accelerations in the fixed frame times m, right? So this term is equals to the F real, right? So and then these two terms with the minus sign will be the Coriolis force and the centrifugal force respectively, right? Okay, so now if we want to study the motion, right? So we want to study the motion of a particle, right? So on the Earth surface, right? So then we will have to consider. So this is the equation of motion that we are going to consider. Okay. So this m dv dt. So now I have no longer worry about the subscript thing here, because from now on, right? From now on, we will only use the rotating frame, right? So then that's why I don't even put the subscript here. So just understand that now this m dv dt, right? This dv dt will always means the acceleration of the particle that observed by us, right? So which the rotating observers. Okay. So and now the real force. Okay, so the real force. So what could be the real forces, right? So the one real force that we will never get rid of would be the gravity, right? So the mg. Okay, so here you can see that I put the g naught instead of just g. I'll explain why, but at least you know what this is. This is the gravitational force anyway. And also here I will specifically put the vector notation here. Okay, and then and I'll explain why, and then plus, right? So all the other forces, right? So the small f, well, depends on what system you have, right? Friction, tension, any other thing. Okay, so then now about the g and the g naught. Okay, so what I want you to consider is the following. Okay, so if you look at this picture here, right? So it's just a cross section of the Earth, right? So I'm just going to assume that the Earth is a perfect sphere to start with, right? So I should mention this earlier, but always just assume that this is a perfect sphere, and the mg naught really would just be pointing exactly to the center of the Earth. Okay, so this mg naught. Okay. So now from this equation, so what I am going to do next is to rearrange one of the terms. So this m omega cross capital R term, I would like to move it up front and put it with the mg naught. Okay, so that's all I did. Put this capital R term with this g naught term. And so this is convenient to do that because this g naught term and this capital R term, you understand that the directions of these terms won't be depending on the motion of the particles. Okay. So remember, so this omega cross capital R term is the versus centrifugal, right? So it's pointing like this, indicated by this red arrow. Okay. And now if I just consider this whole thing together, if I just really try to sum this vector and this vector, and you will get a new vector that is pointing like this one, right? And this whole thing, I will call this mg. And this mg is m times this g naught minus this term. Okay. So then I'm going to call this mg as the so-called the effective gravitational force. Okay. And well, you can see that the direction will be become slightly different, and the magnitude of this g is also slightly smaller than the g naught. Okay. So now you might understand why previously I used the g naught to indicate this, and now I use g. Okay, so this g naught is representing the real value of the g, and then now this g naught minus this whole thing is really the one that we effectively experiencing. Okay. So now just give you an idea. Okay, so the how much is it different from this g naught? Okay, so first of all, you can see that this correction term, well, can be larger or smaller depending on where you are at, right? So in fact, if you're at the equator, right? So then the effect is most significant, right? So because at the equator, then the value that you have for the omega cross r would be the greatest. Okay, but even so, at the equator, so G is about 0.3% smaller than the G naught. And well, what about if you're standing at the North Pole or South Pole? Then you understand that you get any correction. Right? Okay, so therefore, from now on, I will just write the equation of motion in this form. Okay. So we understand that the capital R is basically hidden in this first mg term. Okay. Okay, so I think up to this point, let's take a break. Okay, so let's come back at about 10:30. Okay. Okay, so let's continue. So at this point, if you were not able to exactly follow all the derivation steps to arrive at this result, that's okay for now. Okay, so try to go home and fill in all the details again, but just at least for now, right? So just try to, right? So accept that, right? So this is the equation of motion that we'll be using, and just go back and review the derivation later. Okay. Okay. So now we are ready to really talk about some motions, right? So for the particle, right? So standing at the surface of the Earth, but so the first thing I want to talk about is that if I have just a particle, right? So that is not moving. Okay. So if I have well, actually, so if I have the pendulum like this, okay. So this pendulum, I'm not considering a pendulum that is actually swinging. Okay, so I'm just considering the setup that you have a building, and then you just have a pendulum set up, and then but the pendulum is just at rest. So what is the question here I want to ask is that what is the angle between the string, this line, and the line that is joining, right? So the top of the building to the center of the Earth. Okay. So the top of the building to the center of the Earth, this red dashed line would be what I call the true vertical line. Okay. And remember, so this is the line that goes along with the so-called the mg naught, right? So remember, but in fact, right? So if you set up a pendulum like this, right? So the string actually won't be exactly lined up with the true vertical line. There would be a small angle, and that is due to the centrifugal force. Okay. So in this first problem that I'm considering, so you don't need Coriolis force. You don't need to worry about Coriolis force because this is not moving. Okay, so relative to the rotating frame. Okay. So but I want to find out this angle, which I call epsilon. Okay. So then here, right? So I want to show that this small angle epsilon is actually given by this expression over here. Okay. So if you want to solve this problem, so what do you need is to find out the total force, or the total effective force acted on this particle, right? So because if you, so what would this line be telling you, right? So at the end, right? So if you find out that the total effective force, right? So is pointing like this. Well, the total effective force, what I really mean is that the gravitational force plus the fictitious forces. Okay. And this one will have to be parallel to the string, right? So because in order for this to be at rest, the tension must be balancing the gravitational force and the fictitious forces. Right, so okay, maybe so then this not so 100% correct to say that this is the total effective force, because if I want to talk about the total effective force, that should already include the tension. But you understand that the total effective force, it means the gravitational force plus the fictitious forces. So tension. Okay, so therefore, what I really want to do is to find out the direction of this F effective and to see how much is it deviated from the Z direction. Right? So that is, you will find that this F effective will have some X component. Okay, so not just the Z component. Okay. So the F effective, right? So you know what that would be, right? So the mg naught, right? So and minus the centrifugal. Okay. Okay, so now, first of all, right? So even without doing this cross product, you understand that the centrifugal force is pointing this way, right? So away from the rotating axis, right? So but as a practice, we will actually do the cross product explicitly together, but this is to this way, right? So the F centrifugal. So again, we remind you how I set up the coordinate system, right? So it's like this. I really should have drawn these two things at this point, right? So but I don't have enough space here, right? So let's say, right, so this is the origin of our coordinate system. Okay. Okay, so what is this G naught? Where is it pointing to? Right, so strictly speaking, this G naught is pointing like this. Let's see. It should be pointing along this line. In principle, right? So this is should be like this. So it will be not actually it will not be exactly along the z hat, right? So as you can see, right? So because this one by itself is not also not parallel to the red dashed line, but here I will make an approximation. Okay, so we'll make an approximation, just saying that this G naught is just roughly parallel to the z hat. Okay. So that is to say, I'm going to just say that this is the first term is just minus mg naught z hat. Okay. Approximation is made here. Okay. So then now let's deal with the second term. Okay. So the m omega cross r. Now I want to express the omega vector, okay, using my coordinate system. So how do I do that? Well, so what is omega? So omega would be a vector like this, right? So let me draw another picture which is a bit more clean, right? So omega is a vector like this, and I want to express omega in terms of this x hat and z hat, right? So omega is like pointing like this. And this is lambda, right? So that's why this is also lambda. No, I'm sorry. This is not lambda. This is 90° minus lambda, right? So because this is lambda, this is right. So pi over 2 minus lambda, right? So that's why this is also pi divided by 2 minus lambda. Okay. Right. So therefore, what is omega? So omega, if you just work out the two components, at the end you'll find that it would be minus omega times the Like this. Okay. Right. So if you just see the two components, break down the two components by yourself, you should be able to get that this omega vector is given by this. Okay. Okay. So then now I'm going to plug it back here. Right. So I want to work out the cross product. Right. And what about the R, capital R vector? Right. So the capital R is the capital R vector is this thing. Right. And this capital R vector is just parallel to the z hat, right? So then therefore this capital R vector is just R times z hat. Okay. Okay, so now if you want to do the cross product, right? So then what you need to do is just using the determinant. Right, like this. And then this would give you R omega cosine lambda y hat. And then of course you need to do the cross product one more time. You need to do omega cross this one. Right, so in order to get to the omega cross R. Okay. But okay, so I'll just skip the steps. But omega cross R, you should be able to find that this is this one. Get a square. Like this. Okay. Okay, so therefore, now you can see that I have actually a minus here. I have the first term only have the z component, right? So and then I have the second term which has both x component and the z component. Right. So therefore, don't run out of space, but let me just write the whole result here. Okay. Now have a plus sign here. Okay, so then this angle, right? So this epsilon, right? So how do we find this? Right. So we know that the tangent of this epsilon, right? So would be just the ratio between the two components, right? So that would be the ratio between the x component and the Z component. Right. So, and the X component is this term, right? So the Z component would be this term plus this term. Then that would give you this ratio. Okay. And of course, I'm also making an approximation that tangent, this because it's very small, so epsilon is roughly equals to tangent epsilon. And this one just given by this. Okay. Okay, so now, right, so you understand that the line of the effective the plumb line, right? So that the plumb line that I that's how I call it, the plumb line would be not exactly parallel to the true vertical line. Okay. So now from now on, right? So in the upcoming problems, okay. So what we are going to do is that I'm going to just imagine that you are going to slightly tilt this coordinate system. Okay, so such that, let me do it here. Let me do it here. Right, so from now on, we're going to just imagine this, you're slightly tilting the coordinate system such that the z hat, right, the z hat is just parallel to the plumb line. Okay. So that is to say, I want to kind of make the z hat to be parallel to the effective gravity acceleration due to gravity. But anyway, so this is just a very small correction. Okay. Okay, so next we are actually going to consider a particle that is moving. Okay, so that is moving in the rotating frame. Then that's how the Coriolis force come in. Okay. So in principle, so we have already derived the most general form for the equation of motion that we need to solve, right? So, but in the examples that we are going to talk about, it will be either just a projectile motion or a free falling motion. So that is, there won't be any other tension, any other friction, and so on. Okay, so we are the only real force that we are going to consider would be the mg. Okay. So then that is our goal in the upcoming examples would be solving this equation, right? So in principle, with this equation. Okay. So, however, right, so in general, this might be difficult, and what we are going to do first is to neglect the last term, okay, the centrifugal term. So then the equation of motion is simplified like this. Okay. So, but be very careful here. When I say that we neglect the centrifugal term, right? So mathematically, I mean I'm dropping this last term, right? So, but remember, the main part of the centrifugal term is already included over here. Remember, the capital R term is included, is hidden, is this mg term already. So therefore, even we are dropping this term, okay, so we are actually still including a majority part of the centrifugal effect, right? So because the omega cross r term is here, that is much bigger, right? So it's hidden in this, and clearly this term is much bigger than this term anyway, right? So this is the capital R, right? So distance between the Earth center and the Earth surface, and on the other hand, this is just a small r, very small. Okay. So just remind you, okay, so even I'm dropping this term, doesn't really mean that I'm completely ignoring the centrifugal effect. In fact, I'm still keeping the main part of the centrifugal effect. Okay, so then this is the equation that we are going to solve. So in principle, so we can solve this equation exactly. So it won't be too hard. I'll show you a bit later, but you can kind of imagine what you need to do, right? So all you need to do again is to, right? So this omega, right? So first of all, this omega would be this one. Right, and then this V, right? So again, you just, as usual, you just write it this way. Okay, so if you try to just substitute this one to the equation and also this one to the equation, right? So then you imagine that what you are getting a set of equation that looks like this. Okay, so mx double dot equals to some terms, and the terms will actually depends on well, x dot, y dot, z dot, okay, some of them, and then y double dot also, z double dot also. So if you really want to solve it exactly, you need to solve this system of ODE, right? So and in fact, it can be done, right? So because the whole system is still a linear system, and it can be done without too much difficulty. However, we in the following examples, we won't be doing it this way. We won't be actually trying to find the exact solution. Instead, we are going to find the approximate solution. Okay, so using the so-called one kind of the perturbation calculation, or the so-called the perturbative calculations. Okay, so I'll just use the example to illustrate how it works. Okay, so I'm going to consider an experiment like this. Okay, just someone dropping a ball. Okay, so from the top of a building. Okay, of height h. Okay. So this is the plumb line. Okay. So if we don't consider the Coriolis effect, okay, so you'll find that this ball will just follow this straight plumb line and then reach the ground at this point. However, if we consider the Coriolis force, this ball will be deflected along the way, and then at the end, it will reach the ground at this point. Okay. So, and you can see that there is a distance, right? So this is a delta y. So we want to find the how much this delta y is. Okay, so this is what I call the horizontal deflection. Okay, and this horizontal direction is along this y, and along this y, that means it's either to the east or to the west. Okay, to the east or to the west. So in principle, how do we find out this delta y? Right, so you just need to, in principle, you just need to go back to this equation, solve it, right? So with the initial condition, that what is the initial condition that we have? Initial velocity being 0, right? So, and also the initial position being at some height, right? So you can then exactly solve this out. Okay. So, but what we are going to do, the procedure is the following. Okay. So we are going, we know that the correction or this deflection would be a very, very small number. And that is because this term is actually much smaller than the first term. Okay. So then what it means is that, okay, so if I solve the equation of motion without the second term, right? So that if first of all, if I solve the equation of motion without this second term, well, we all know how to do this, right? So, and in this case would be a straight vertical line falling down, right? So then that is here we solve out. Let's say we already solved solution like this. I call this V naught T. And then now I'm going to consider this term. And when I consider this term, right, so instead of treating this term as an unknown, I'm going to just replace this V by the V naught T that we just obtained. Okay. So like this. Then what you would realize is that this term is known and is small, and it will cause a correction, okay, so to the straight trajectory itself. So that is to say, first of all, you cover the second term, you solve the equation one time, you get the so-called V naught T, and then you substitute the V naught T to this second small term, and then solve it again, and then to obtain the so-called what I call the V1T. Okay, let's say. So the procedure is the following. Okay, so without, right, so the effect of the Coriolis force without the second term, this is the solution. Okay, and right, just V equals U minus GT, right? So U, the initial velocity is 0, so just minus GT Z hat. And then you know that the time taken for this to drop to the ground is this one, square root 2 capital H divided by G. Right, so then now I'm saying to the first order correction. Okay, so then I'm going to, right, so as I said, right, so substitute this v naught back to this term. So then this is what I'm doing. So this term here, right? So given by this determinant, okay. And the cross product, this cross product is along the y direction, okay. And this force, right, so will give rise to the acceleration in the y direction, right? So that's why I have this y double dot to be given by this. Okay. And I want the value of y when the ball reach the ground. That is, I want the value of y at e equals capital T. Okay. So from here, y double dot equals this one. First of all, I obtain y as a function of time by integrating y double dot twice, and then I substitute capital T, okay, so into this function. And then I got this deflection, okay, so like this, okay. So see how it works? So if you don't care about Coriolis force, you get this straight line like this, right? And with some v naught t. And then now you substitute this v naught t to the second term, the Coriolis term. And then you find that the Coriolis force will be along the y direction, right? And then at the end, you will find that the trajectory will look something like this. Okay. So, and as I said, right, so this is not the exact correct solution, right? So this is the approximate solution only. And because after all, this term itself should not be v naught t, it should be really the real v of t. Okay. So actually, let me then do a more systematic description here. So it's in the appendix of the lecture notes. Okay. So what we just did is that we start with this equation. As I said, I dropped this omega cross omega r term, right? So if you actually go to substitute the explicit form of the omega and v, you get these three equations. Okay, so you can see that x double dot depends on y dot, y double dot depends on z dot and x dot, and then z double dot depends on y dot. Okay. So the coupled equation. So no approximations have been made yet. And now from here, if you integrate both sides once, then you got this. Okay, x dot equals something times y plus ux. Ux is the x component of the initial velocity. And then similarly, you get the other two equations. Okay. And also, up to this point, no approximation have been made yet. Everything is exactly correct. Okay. So now it's just that from here, right? So how do I solve for x as a function of time, y as a function of time, z as a function of time. Okay. So, and what we did just now is actually is the following, right? So we first consider pretend that there's no Coriolis effect, right? So, and then that is we set omega equals 0. Then what you would find is that this x naught dot is ux, right? This y naught dot is uy, and this z naught dot is uz minus gt. Okay. This subscript naught, right? So indicated that they are the so-called the zero order solution. Okay. And then now we substitute this zero order solution. Okay. So back to this exact set of equations. Okay. So then I'm getting this. Okay. Right. So you can see that. So this is exact. This is a zero order solution. And then here is the approximation that we are making. Right. You can see that the right hand side, I'm putting it the subscript 0. Okay. And then from here, you can solve it easily. Right. So for example, in the free falling, this page is wrong. In the free falling particle, right? So this is what we have. Okay. And then you just do the integration and do this. Okay. So in fact, as I will show you later, if you want to do a more and more accurate approximation, then what you do is that you substitute this first order solution. So without any correction, I call this a zero order solution. Right. So after that procedure, with the correction, I call this the first order solution. But as I said, right, so this first order solution is still not the exact solution. So what I do is that I substitute this first order solution back to the set of the equation again, and then solve it again. Then you get the so-called second order solution. And then you can keep doing that. Right, so to get the so-called higher and higher order solution, or higher and higher order approximation. Okay. And in principle, right, so you are approaching closer and closer to the real exact solution. Right? So in principle, that's what's going on here. But what you realize that is that every time you do a further step, okay, so the improvement that you get is getting smaller and smaller. So then now let me also show you how to do the second order solution. Then we'll end here. Okay. Okay, so before going to that, I just want to mention that some real number. So if you have a building that's 100 meters tall, and then you drop the ball, and if you are at this latitude, then the deflection that you get about 1.55 centimeter, very small. So although this is a very, very small number, but actually it has been verified experimentally. Okay. Okay, so now, as I said, right, so this is the first order correction, or the first order solution that we got. Okay. Right, so it's mostly So it's this curve now, right? So it's the green one, right? Well, this is the position as a function of time, but this is the velocity as a function of time, right? So this is, so the velocity mostly is still in the z direction, in the vertical direction, but with a little bit in the y direction, right? So that's why it's deflected. So now I'm going to, right, so put this to the Coriolis term again, right? So do the cross product one more time. Then, well, so now you see actually getting more complicated. Okay, so x, y, z component coming out. Okay. So now you see that there is a x hat term. Well, that this is new, right? So you didn't see this in the first order calculation, right? So in this picture, you just have this deflection in this way. So that is if you consider one higher order correction or one higher order solution, you see that the deflection is actually also a little bit out of the page, right? So along the x direction. Okay. And that is given by this term, right? So that is, right, so the x double dot is given by this term over here, and then the x as a function of time is given by this one. So now, well, so you can see that actually this term depends on omega square. Okay. So in the previously, right, so this depends on omega. Omega and omega square. So you actually understand that omega is a very small number. Okay. Right. So it takes a day for the Earth to complete one full revolution. Right. So if you just try the omega, plug in the real number, just express omega as radian per second, then you get a very small number. Right. So therefore, right, so omega is a very small number, then omega square is an even much smaller number. Right. So then this second order correction, so along the x direction, depends on omega square, and this you can imagine that would be much smaller than the first order correction, which depends on omega. So then you can kind of see that, right? So the second time that I do this approximation, I get a solution that is actually even closer to the real one, but that you realize that the second order correction is very small. Okay. And you can keep doing that. You realize that the next order of correction you get would depends on the omega to the even higher power. Right. So then you will start to think that it's not really necessary, right? So to do the correction that many times, right? So because the correction term that you are getting is just getting more and more insignificant, not so useful practically. Right? So anyway, so in our example, so we'll never go beyond the second order correction. But you imagine that you can do that, right? So all you need to do is that you just substitute the V2T, right? So back to the Coriolis term again and repeat the same calculation. Okay. Okay, so I think I have to stop here. So next time we'll finish this part of the chapter. Okay.